Packet forwarding is at the heart of how IP enables communication across networks. When sending data between hosts or routers, IP relies on the forwarding capabilities of local networks, which use Layer 2 mechanisms. Packets are encapsulated in Layer 2 frames and transmitted based on MAC addresses. There are two scenarios. Direct forwarding is used when the destination is in the same IP network. Indirect forwarding happens when the destination is outside the local network. In this case, the packet is sent to a router for further forwarding. In the next slides, we'll explore how this process works differently when the forwarding happens in a host versus a router. When host B needs to send a packet to host A, it first checks whether the destination IP address belongs to the same subnet as its own. By applying the subnet mask, here /24, B recognizes that both IP addresses fall within the same network. Since the destination is in the same IP network, direct forwarding is possible. Host B will resolve A's MAC address using ARP and then send the packet directly to A at the data link layer using that MAC address. No router is needed for this local communication, and we will see later how RP works. Once B confirms that A is in the same subnet, it checks its IP MAC correspondence table. That is a table mapping the IP addresses to MAC addresses to find the MAC address corresponding to A's IP. If the entry is already in the table, B retrieves MAC A directly. If not, the ARP protocol will fill this table accordingly. Then, B passes the packet to the data link layer, where it is encapsulated in a Layer 2 frame with MAC A as the destination. This frame is then transmitted directly over the local network to host A. Once the MAC address is resolved, host B prepares the frame for transmission. The IP packet, containing the source and destination IP addresses, is encapsulated within an Ethernet frame. This frame includes Layer 2 headers, setting MAC B as the source and MAC A as the destination. The encapsulated structure is then sent over the local network. When host A receives the frame, it reads the IP payload and recognizes that the packet is addressed to its own IP, allowing it to process the data accordingly. What happens when the destination host is not in the same network? Host B needs to send a packet to a destination that is outside its network. By comparing its own IP address and subnet mask with the destination IP, it determines that the destination lies outside its local network. Since the target is not reachable directly, host B must forward the packet to its default gateway. That is the router C. Since the destination IP is outside host B's network, it needs to forward the packet to its default gateway, router C. To do that, B looks up the MAC address of the router in its IP MAC correspondence table. Once retrieved, B passes the packet down the stack. The IP packet remains addressed to the final destination, but the frame is built with the router's MAC as the next hop destination at Layer 2. After resolving the router's MAC address, host B constructs the full packet. At the network layer, it sets the source IP as its own and the destination IP as that of host D. Then, at the data link layer, it encapsulates the IP packet in a frame, using its own MAC as the source and the router's MAC as the destination. This frame is then transmitted over the local interface, completing the process of indirect forwarding from a host. This screenshot shows a typical host network configuration. The IP address, subnet mask, and default router, also known as the default gateway, are all automatically assigned via DHCP. The default router serves as the next hop for all traffic destined outside the local subnet. The subnet mask defines the network boundary, enabling the host to determine whether to use direct or indirect forwarding for outbound packets. Routers are dedicated internetworking devices that operate with multiple interfaces, enabling them to connect and forward packets across different networks. Like hosts, they implement both direct and indirect forwarding. However, in the case of routers, direct forwarding occurs when the destination is reachable through one of the router's directly connected interfaces, such as IP-A, IP-B, or IP-C, shown here. Indirect forwarding instead relies on the router's forwarding table, which specifies the next hop and output interface for destinations not directly connected. This routing logic enables efficient packet delivery across complex topologies. Routers perform forwarding between entire IP networks, using the NetID portion of the destination IP address. They don't examine individual host IDs. Instead, they rely on routing table entries that map entire networks to interfaces. For instance, if a packet is destined for network 2 router B forwards it through the interface connected to network 2. All hosts in that subnet are effectively represented by a single entry. This aggregation reduces routing complexity and improves scalability. CIDR allows flexible subnetting by using variable length net masks, but it also requires that routing tables explicitly specify the net mask for each route entry. Without this, routers wouldn't know where the NetID ends and the hostID begins. That's why routing protocols must advertise both the network address and its associated net mask, so that routes can be correctly interpreted and aggregated. This example illustrates how routing tables use CIDR prefixes to forward packets. Each entry defines a destination network using a prefix and net mask, a next hop IP address, and the output interface. To decide between direct or indirect forwarding, the host checks if the destination IP is in the same subnet. This is done by applying a bitwise AND between the IP address and the net mask. In this example, the interface IP AND and the net mask gives an IP network as result. We do the same for the destination IP, and we get the same result. Because the results match, the host knows the destination is in the same subnet, so it uses direct forwarding without going through a router. This simple check is how IP decides whether to send a packet locally or via a gateway. When direct forwarding isn't possible, meaning the destination is not in the same subnet, the router checks its routing table to decide where to forward the packet. It goes through each entry in the table, applying a bitwise AND between the destination IP and the net mask for that row, just like we saw before. If multiple entries match, the router selects the one with the longest prefix, which is the net mask with the most ones. This is known as the longest prefix match rule. In this example, the destination IP matches 3 routes, /8, /16, and /24. The /24 entry is the most specific, so the packet is forwarded using route 3. This ensures that the packet takes the most precise path possible in the network. This example shows a more detailed routing table listing network prefixes, net masks, and the corresponding next hops. When a router receives a packet, it tries to match the destination IP against each row by performing a bitwise AND with the net mask. If multiple rows match, it chooses the most specific one, the one with the longest prefix. But what if none of the rows match? That's where the default route comes in. This last row will match any address, since the net mask is 0 bits long. It's a kind of catch-all rule used when no better match is found. So in essence, the default route ensures that packets don't get dropped just because no specific entry exists. It acts like a last resort path. Let's look at an example of how a router uses its routing table to forward a packet. Suppose a packet arrives with the following destination IP. The router checks this address against each entry in the table using the associated net mask. When it reaches the first row with a /24 net mask, it doesn't match. But then, it finds a match with the third row, which includes the destination address. That row points to next hop, so the packet is forwarded there. The router uses interface 1, which is in the same subnet as the destination, and everything checks out. Now let's walk through a second routing example, this time with another destination IP. The router checks the routing table row by row, performing an AND operation between the destination IP and each net mask. We have a match in the second row. This one matches, and it's also the longest prefix match, meaning it gives us the most specific route. So, even though the default route at the bottom would also technically work, the router chooses this one because it has the most bits in the net mask. The packet is forwarded via the corresponding next hop. In this example, the router finds 3 matches, one with /24, one with /20, and the default route. Among these, the most specific, or longest prefix match, is the one with /24. This is the route the router chooses, because it offers the most accurate path to the destination. The packet is forwarded to the corresponding next hop, as indicated in the routing table, and again, this will use interface 1. Let's now consider this destination IP. As we scan the routing table, none of the specific entries match this destination. All the comparisons return a negative result, meaning the destination doesn't belong to any of the explicitly listed network. In this case, the default route is used.